Welcome back to the deep dive. Our goal here is to take those, the deepest cuts of knowledge, the articles, the internal research notes, the technical guides, and really just distill them into immediate, actionable insights for you.
hmm
Today, we are diving straight into the engine room of decision making. We're asking, how do we know if our experiments are actually telling us the truth?
It's the perennial challenge, isn't it? Especially in product development and data science. You launch a new feature, you run an A/B test, and the numbers come back flat.
Right.
And you're left to this moment of ambiguity. Was the feature truly bad, or, was your test simply incapable of finding the benefit? And that ambiguity, it just paralyzes product roadmaps.
Absolutely. When teams lack confidence in their results, the pace of innovation, it just slows to a crawl. So our mission today is to decode that core triad that ensures confident experimentation.
Statistical power, sample size, which we'll call N, and the minimum detectable effect, or MDE.
Exactly. We've synthesized the crucial study notes and the visual aids discussing these A/B testing metrics, really the blueprints for valid testing, and we're translating those statistical constructs into strategic planning tools.
That's the key. The ability to pre-calculate the required sample size and, the necessary duration of a test is the single most important planning step. If you can't estimate N,
Then you can't estimate the time.
you can't estimate the time, and without a time estimate, you can't align your product goals with business cycles.
Yeah.
It moves experimentation from like an art form to a science of resource allocation.
Okay, let's unpack this core tension right away. If you run a test, let's say you're testing two slightly different recommendation algorithms, and after 2 weeks the metrics look identical, you have a crucial question.
hmm
How do you truly know if the failure to find a difference means the new algorithm is ineffective, or if your test just wasn't, well, powerful enough to isolate the signal from the noise?
And the answer to that is found in the concept of statistical power. Simply put, power is the probability that an experiment will correctly detect a real effect if that effect genuinely exists.
Yeah.
It's like your test's competency score.
So if that new recommendation engine is truly generating, say, a 4% lift in user engagement, power is the mathematical chance, the probability that my experiment will correctly come back and say, yes, the new engine is better.
That's it. And the standard default we see across, well, most of the technology industry, and what our sources confirm, is aiming for 80% power. This is the consensus balance point.
What does that mean, though, balance point?
It means we accept a 20% risk that a genuine improvement is present, but our test fails to find it.
20% seems high, though, doesn't it? I mean, if I'm a high-growth startup, shouldn't I demand 95% power? If I'm willing to spend the money to build the feature, why would I risk missing 1 in 5 potential wins?
And that is a critical strategic question. The 80% default, it's less about statistical purity and more about economic practicality.
Okay.
If you demand 90% power, you dramatically increase the required sample size, and that increases the testing duration and the opportunity cost exponentially.
Oh, wow.
If a test takes 1 month at 80% power, it might take 3 months at 95% power. The engineering team might have to sit idle, or you sacrifice 3 months of learning velocity across your entire product portfolio.
Oh, just to reduce that risk from 20% down to 10%.
Exactly. We have to weigh the cost of being slow against the cost of being occasionally wrong.
Let's start with the immediate consequence of neglecting power. If a product manager gets impatient and decides to run an underpowered test, say only 50% power, what is the immediate measurable impact on the business?
The impact is profound, and we
Yeah.
see this mistake generating noise in product reporting constantly. First, you're on a dangerously high risk of false negatives,
Oh, okay.
or as statisticians label the type 2 error, which is beta. This is the failure to reject the null hypothesis when you really should have. You declare no difference exists, but a positive, profitable difference was there.
That means we actively throw away a good feature. Or maybe we roll it out anyway based on gut feeling, but without any trustworthy data to back it up, we just lose that actual quantified business value.
Exactly. You are leaving money, time, or engagement on the table. And the second critical issue is that low power leads to, well, noisy and highly unstable results.
Meaning the numbers are all over the place day to day.
All over the place. With insufficient data points, the daily results of the experiment will oscillate wildly. One day, the variant is up 10%, the next, it's down 5%. This volatility erodes trust. A product manager cannot make a multi-million-dollar investment decision based on data that shifts radically every 24 hours.
So the goal of aiming for adequate power, usually 80%, is about engineering stability. It's a mechanism for guaranteeing that if a feature genuinely improves user behavior, the experiment has a strong, predetermined chance of detecting it accurately and consistently. It gives us a robust signal.
It is the foundation of data integrity. And to really internalize this, we have to look at the geometry of hypothesis testing. This is where the visualization in the source material, those two overlapping density curves, becomes, indispensable.
Okay, let's sketch this out mentally for everyone listening. We've got two overlapping bell curves on a graph. The red curve is centered at the null hypothesis H0, which assumes no difference exists.
Right. And the green curve is centered at the alternative hypothesis H1, which assumes a real effect exists.
Okay, two curves, got it.
Correct. The first element we set as experiment designers is the decision cutoff. This is a vertical line on the graph. If our observed test result falls to the right of this cutoff, we mathematically decide to reject H0 and declare the variant the winner.
And I see this little orange area under the red H0 curve past that decision cutoff. That's the risk we accept when we make that decision, right?
That orange area is our significance level, or alpha. This represents the chance of detecting a difference when one does not exist, a false positive or type I error.
And we usually set that at 5%.
Typically fixed at 5% or 0.05, which correlates to a 95% confidence level. We tolerate being wrong 5% of the time, accepting that, 1 in 20 tests might show a false winner.
Now, moving to the green curve, H1, which represents the world where the new feature actually works. The large green shaded area under H1 that falls to the right of the decision cutoff, that's the gold standard. That's our power.
That is power, or 1 beta, the probability of a correct detection. If we set it at 80%, that green area covers 80% of the H1 distribution.
And the little bit left over.
Conversely, the small, unshaded area of the green curve that still sits to the left of the cutoff, the part that overlaps the H0 curve, that is our type 2 error, beta. That's the false negative risk, the 20% we accept.
This visualization is so powerful because it immediately introduces the MDE. The distance between the mean of the red curve and the mean of the green curve, that separation, that is the minimum detectable effect. It's the physical manifestation of the size of the improvement we are looking for.
Precisely. If the MDE is large, the green curve is physically shifted far away from the red one, which minimizes the overlap. This makes it easier to achieve high power with a smaller n.
And if the MDE is tiny?
If the MDE is tiny, the curves are nearly stacked on top of each other, overlapping heavily. To push that power area up to 80%, you need an enormous sample size to shrink the width of those curves.
Wait, you said shrink the width. If MDE is the distance between the means, what exactly controls the width of those individual bell curves?
That's the key statistical lever we often forget about, variance, or the standard deviation of the data. Variance is a measure of how spread out your data points are. If your variance is high, your bell curves are wide and flat, leading to much greater overlap between H0 and H1, regardless of the MDE.
So a high variance metric like daily revenue per user, which is hugely variable, requires much, much larger samples than a low variance metric, like a simple button click-through rate.
Exactly.
Because the wider curves demand more data points to confidently separate them.
Exactly. The sample size calculation inherently takes this variance into account. So to reduce false negatives, which means increasing power, you essentially have 3 major strategic levers. 1, increase the MDE.
The curves further apart.
2, decrease the variance.
The curves skinnier.
And 3, increase your sample size, which mathematically helps shrink the effective width of the curves.
This visualization leads us perfectly to the practical application. If we want to calculate the required sample size, n, before we launch, what are the 4 non-negotiable pieces of information we must input? These are the 4 pillars of sample size determination.
These are the core variables you manipulate in your planning process. Number 1, the baseline rate, P1. Yeah. Your current performance metric. You have to know this accurately.
Okay.
2, the minimum detectable effect, or MDE. This is the smallest lift that matters to the business. This is the strategic choice.
Right.
3, the significance level, alpha, which is almost always fixed at 0.85. And 4, the power, 1 beta, almost always fixed at 0.80 or 80%.
So once we have 3 of those fixed, say the baseline, alpha, and power, the size of the MDE we choose immediately dictates the 4th, the sample size, n. It's a closed system, a trade-off curve.
It is. And once those 4 pillars are defined, we have to look at the dynamics. Understanding what manipulates power is critical for troubleshooting infeasible tests.
Okay, let's unpack the key ways to boost power. Running the test longer for a larger sample size n is sort of the brute force method, but what are the strategic ways?
Strategically, the most direct lever is choosing a larger MDE. If you are looking for a massive, disruptive 15% change, your test needs far less statistical sensitivity. and thus fewer users, than if you're looking for a marginal 1% gain.
So the size of the effect you're looking for is inversely proportional to the sample size you need.
That's a great way to put it. And connecting back to our discussion on the curve width, anything that causes the variance to decrease will increase power. This could be selecting a highly stable metric, running a test on a tightly defined user segment, or focusing on high-frequency events.
So tighter data means narrower bell curves, and power goes up.
That's right. And finally, as the sources note, power is statistically easier to achieve when baseline rates are not extremely low. Trying to detect a tiny change on an event that happens, once in every 1,000 user sessions is incredibly difficult because of the low signal-to-noise ratio.
So if those four variables are fixed, the most common mistake is trying to measure a small effect, a low MDE, using a very noisy, low-frequency metric.
A high variance metric, yeah.
Which leads inevitably to the default state of low power and inconclusive results.
It guarantees a statistical headache. Let's zoom in on the MDE, the minimum detectable effect, because this is the operational decision product managers have to defend their leadership. It's the smallest uplift that is worth the business investment and that the experiment is designed to detect.
I appreciate that framing. MDE isn't just some number that a calculator spits out, it's a financial threshold. If a lift below the MDE doesn't justify the engineering salaries, the opportunity cost, the ongoing maintenance, then statistically detecting it is just a fun fact, not a business outcome.
Precisely. Let's ground this in reality. Imagine a company has a new personalization feature they estimate will take, $100,000 of engineering time to build and maintain over a year.
Okay.
If their baseline conversion is 12% and their internal financial model shows they need a 2.5 percentage point lift to recoup that $100,000 and turn a profit, then 2.5 percentage points is their MDE.
So their experiment has to be powered specifically to find that $100,000 difference, or they risk rolling out an unprofitable feature.
That's the logic. And this brings us squarely to the PM trade-off: sensitivity versus speed. It's the constant tug of war in every agile development sprint.
It's the strategic heart of the planning process, really.
Yeah. If the PM demands a small MDE, say a 1 percentage point lift, they gain high sensitivity, they won't miss any valuable marginal gains.
Yeah. But the calculator is going to mandate a huge N.
A very large N, resulting in an experiment that could take months. This significantly slows down the entire product cycle.
And conversely, if they choose a large MDE, say a 10 percentage point lift,
the experiment is quick and cheap in terms of required traffic. They get an answer in days, not months. But they carry the risk of missing valuable, meaningful gains, say a 4% uplift, that could still have paid for the feature 10 times over.
So the medium MDE zone, maybe 3 to 5 percentage points, that's usually the good balance.
Typically, yeah. But to truly understand the consequence of this choice, we have to analyze the visual cost, the exponential nature of the trade-off shown in the power curve graph.
Okay, let's dedicate some serious time to this power curve graph. It's labeled Power versus N by Diff. This visualization perfectly captures the economic reality you just described. We see power on the vertical axis from 0 to 1.0 and sample size N on the horizontal axis.
Yes. Now, this chart is a specific example, and the underlying parameters are critical. The visualization is based on a two-sided McNamara test with an alpha of 0.05.
What's a McNamara test?
For our informed audience, it's a specific statistical test, often used when you have paired data like measuring the same users before and after a treatment, or comparing click-through rates on highly related events. The choice of test and the data distribution it assumes heavily influences the shape of these curves.
And there's another parameter noted here. PD equals 0.300.
The PD, or probability of difference, being 0.300, tells us the baseline variance or baseline conversion rate used for this model is relatively high, around 30%. Remember, high baselines generally require lower N than very low baselines, but the fundamental exponential cost remains clear across the three curves plotted.
Right, we have the blue, the green, and the red curve representing different MDEs, or diffs.
The blue curve is for a large difference. Diff equals 0.200. The green is a medium difference. Diff equals 0.150. And the red is for the smallest effect we are trying to detect. Diff equals 0.100.
And the core insight to hammer home here
is that the NDE decreases exponentially slower than sample size increases. This means every incremental demand for higher sensitivity for smaller MDE costs you a disproportionately massive chunk of traffic and time.
Let's follow that cost precisely. If we look at the blue curve, the 0.200 diff, which is a massive 20% uplift, to hit our standard 80% power, we need maybe 50 subjects per group. This is a very quick test.
A very quick test. Now, look at the green curve, the 0.150 diff. We've only reduced the desired uplift by a quarter, but the required sample size to hit 80% power jumps sharply to about 150 subjects. That's already triple the traffic.
And the red curve, the small effect, diff E0.100, shows the dramatic penalty.
Oh.
We've roughly halved the MDE from the blue curve, from 0.2/00 down to 0.1000, but the required N to achieve 80% power explodes to over 300 subjects.
This is the critical takeaway for product leadership. Cutting the desired MDE in half can necessitate 6 times the sample size to maintain the same confidence level. This cost is driven by the statistical reality that N is determined by the square root of the number of observations needed to overcome the inherent variance.
You have the effect size. You quadruple the required N.
Exactly. The flattening curve demonstrates this quadratic or exponential relationship.
And it gets even more painful when leadership, unsatisfied with 80% confidence, demands 90% or 95% power. Looking at that red curve again, the 0.1001, to move power from 0.8 to 0.9, you're looking at increasing N from 300 users toward 500 or more. The curve is practically horizontal in that upper range.
That flattening is the statistical impossibility of perfect confidence. It confirms that chasing marginal gains in power, moving from 90% to 95%, costs an unrealistic, disproportionate amount of time and traffic. The difference between 95% and 100% is effectively infinite traffic.
Wow.
The 80% standard is the strategic acceptance of that economic reality. It's the point where the cost of increasing power begins to outweigh the benefit of slightly lower type 2 error risk.
This makes setting the MDE the most powerful resource planning tool a PM has. If you can't afford the time dictated by that curve for the MDE you want, you simply cannot run the test as planned.
Period.
We've established the strategic stakes and the theory. Now, let's make this concrete. How do we turn these 4 pillars into a definitive calculation for N? We need to talk about the real-world tools people use.
Data scientists and PMs rely on industry-standard tools, such as the widely referenced Evan Miller A/B testing calculators. These tools operationalize the complex mathematical formulas behind the bell curves into a usable interface.
And we mainly use 2 of them.
We primarily use the sample size calculator to plan and the power calculator to evaluate existing tests.
Let's detail the 4 specific inputs a PM must supply to calculate the required sample size before launch.
Okay, they are. 1, the baseline conversion rate, P1. 2, the expected conversion rate for the variant, P2, which is simply P1 plus the chosen MDE. 3, the significance level, alpha. And 4, the desired power level.
Let's walk through the example from the study notes to see this calculation in action and then immediately run a feasibility check.
Okay. Step 1, determine baseline. Our metric is checkout conversion, and it's currently performing at 15%, so P1 is 0.15.
Step 2, choose MDE. Based on business value, we decide anything less than a 3 percentage point uplift isn't worth rolling out. So our MDE is plus 3 percentage points. That means our expected variant conversion rate is 18%.
Right, P2 is 0.18. Step 3, set confidence and power. We stick to the defaults.
Yeah.
Alpha, 0.05 for 95% confidence, and power equals 0.8.
And step 4, calculator output. We plug in P1 0.15, P2 0.15, alpha 0.05, and power 0.80. The tool calculates the required N. Our notes show this requires approximately 8,200 users per group.
That is a total of 15,400 users minimum. And if the test runs for a day less or a user less than that, the resulting data is statistically underpowered, and that 80% probability guarantee is instantly void.
Let's look at the other example from the screenshot, which shows a much lower required sample size. This really reinforces how critical that MDE choice is.
In that case, the baseline conversion rate was 20%, and the user set a much larger minimum detectable effect of 5 percentage points. They used the absolute MDE setting, meaning they were looking for a conversion rate of 25%.
With the standard 80% power and 5% significance, the calculator returned a required sample size of only 1,005 users per branch.
The difference is staggering, 8,200 versus 1,005. This test is dramatically cheaper in terms of traffic because the PM was only looking for a colossal 5-point win. They sacrificed sensitivity entirely, betting that their feature would be an undeniable home run.
Now for the final, most crucial step. Interpretation and feasibility check. This is where the statistics meet the reality of product traffic. Let's use that 8,200 users per group requirement.
So we need 16,400 total users who are eligible for the test, often meaning they hit the specific page or funnel step being measured. We have to map this required N against our daily traffic volume.
Okay, scenario A. We have a high traffic segment generating 500 eligible users per day in each branch, so a total of 1,000 users daily.
For scenario A, 8,200 users required per group, at 500 users per group per day. The test duration is 8,200 divided by 500, which equals 16.4 days.
So just over 2 weeks.
Yeah, that's long, but 2 weeks is manageable for a major experiment.
Now, scenario B. We are testing a feature on a low-traffic section, say the settings menu or a secondary feature, and we only get 50 eligible users per day in each branch. So 100 users total, daily.
For scenario B, 8,200 users required per group at 50 users per group per day. The test duration is 8,200 divided by 50, which equals 164 days.
164 days. That is over 5 months.
5 months.
5 months. That immediately flags the experiment as infeasible for most product teams. You cannot wait 5 months to decide on one feature. You have to stop, scrap the current design, or choose a new metric.
The feasibility check forces a conversation about resource allocation and strategy before any engineering time is wasted. If the calculation shows 164 days are needed, the PM has an obligation to find an alternative.
That concept of infeasibility is a major obstacle. Let's define the conditions that make a test unrunnable, beyond just a multi-month duration.
A test becomes strategically infeasible if the required sample size mandates a duration that conflicts with the business cycle or the underlying population behavior.
For instance, if the test duration means the results will be distorted by seasonality.
Exactly. If the test requires 4 months, running it from September to January means you are encompassing both the peak holiday shopping and the post-New Year slump. You won't be able to isolate whether the lift came from your feature or the seasonal peak. The data is hopelessly confounded.
And we noted the problem with infrequent user revisits. If the feature is only relevant to users who visit once a month, like a quarterly reporting tool or a bill pay feature, even if you hit your daily traffic number, the N for unique users accrues painfully slowly.
That's a common trap. If you need 16,400 unique users, but your product only sees 1,000 unique monthly users who meet the criteria, your total duration for the test to reach the correct N is 16 months. No PM can wait that long.
When facing infeasibility, the team can't just give up. What are the specific mitigation strategies for these low-traffic environments?
The most common, as we noted, is simply using a bigger MDE. You sacrifice the statistical sensitivity needed for marginal gains and focus only on detecting a huge wind shifting the test from scenario B, the 164-day one, back toward scenario A, the 16-day one, by demanding a 10 percentage point lift instead of 3.
So you're changing the business question entirely. Is this feature a massive success instead of, is this feature a marginal improvement?
Precisely. Other mitigation strategies include using statistical techniques that don't rely on a single decision point. Sequential testing or Bayesian approaches allow for continuous monitoring and adaptive stopping rules.
Meaning you can often conclude the test earlier.
Yes, if the effect is overwhelmingly large, you can reduce the overall time burden compared to traditional fixed horizon testing.
But those require specialized expertise, which leads to the idea of adjusting the metric itself.
Yes. The most practical solution is targeting a subset of traffic with higher event frequency or moving up the funnel. If your conversion is 1%, but add to cart is 30%, you might decide to optimize the add to cart metric, where the volume of events is 30 times higher. This dramatically reduces the variance and the required N needed to find a significant lift.
This brings us to the warning label section, the common pitfalls that even high-performing teams fall into. We've established that running underpowered tests is the single greatest source of noise in quarterly product reporting.
It leads to the statistical equivalent of optical illusions. Inconclusive results force the team to argue about subjective interpretation rather than objective data. It fosters an environment where politics, or the HIPPO, the highest paid person's opinion, triumphs over evidence.
What about simple data entry errors when using these calculators? I can see that happening easily.
Calculation errors are alarmingly common. The number one mistake is confusing MDE percentage change versus percentage points.
Oh, that's a big one.
It is. If your baseline is 10% and you enter a 5% MDE, did you mean 5 percentage points to move conversion to 15%, or did you mean a 5% relative change moving conversion to 10.5%?
The required sample size for those two inputs is vastly different. A 5 percentage point lift is an earthquake. A 5% relative lift is a tremor. Mislabeling the input leads to a grossly inaccurate N.
Absolutely. You must also ensure you use consistent units and, crucially, that you never forget to account for guardrails.
What do you mean by that?
If your primary metric, say click-through rate, requires 5,000 users, but your secondary guardrail metric, say time spent on site, which is a high variance metric, requires 20,000 users to achieve 80% power, you must size your entire experiment for 20,000 users.
Why? Why does the weakest, most variable metric dictate the size of the whole test?
Because you're rolling out a feature only if it passes all your criteria. If you detect a massive lift in clicks at 5,000 users, but you can't confidently say it didn't hurt revenue or engagement until 20,000 users, flopping at 5,000 exposes you to massive risk of a false negative on the critical guardrail metric. The experiment has to run until the necessary power is achieved for the metric with the highest end requirement.
The final major pitfalls concern interpretation, specifically the famous misunderstanding of p-values.
P-values tell us something very narrow. The probability of seeing data as extreme as ours, assuming the null hypothesis, 8.0, is true. Statistical significance of p-value below 0.05 just confirms that a difference exists and that it's probably not random.
But it could be a tiny difference.
It might be a 0.0001% lift, but the p-value confirms it's real.
But that leads to the scenario where a result is statistically significant but too small to matter. It's practically worthless to the business.
Exactly. Or, worse, the significance might be driven by a single, small outlier cohort that happened to behave wildly, leading you to conclude a permanent feature change based on temporary noise.
And the absolute deadliest technical sin in A/B testing. Peeking. Checking the results before N is hit. Why is it so terrible?
It fundamentally invalidates the p-value calculation. The 5% significance level is based on the math, assuming you have one planned decision point, which is when you hit your calculated sample size N.
But people check it every day.
And if you peak daily for 30 days, you aren't running one test, you're running 30 simultaneous tests, and you are vastly increasing your overall chance of finding a false positive purely due to random noise.
So if I peak 30 times, my effective alpha isn't 5% anymore.
No, your family-wise error rate could skyrocket to 20% or more. If you see a random fluctuation on day 7 that dips below the 0.05 threshold and you stop the test, you are almost certainly declaring a false winner that would have regressed to the mean if you had just kept running it until N was achieved.
So statistical significance must only be assessed at the predetermined stopping point.
Only. And finally, the technical pitfall regarding traffic distribution. Group imbalance. If the control group accidentally receives 60% of the traffic and the treatment group only 40%, the overall power of the test is immediately compromised. The power calculation assumes maximum efficiency, which is achieved when the sample sizes for control and variant are roughly equal. Any imbalance reduces the effective N and decreases your sensitivity. You need rigorous infrastructure to ensure an equal traffic split.
If we synthesize everything we've discussed, the product manager's job shifts from merely interpreting results to strategically designing them. This is the PM's decision framework regarding power and MDE.
It is.
It sounds like the PM needs to act as the chief economist of the experiment, balancing statistical requirements with financial reality.
That's the perfect analogy. They must choose the MDE based on tangible business value, not statistical idealism. If the engineering cost requires a 4% lift, they set MDE at 4%, even if they know a smaller test could detect a 1% lift. Why spend the traffic and time detecting an uplift you won't roll out anyway?
And the discipline around underpowered tests that has to be absolute.
Absolutely. The rule is to use the calculators early during the planning phase. The calculation should happen before the feature is prioritized. If the calculation mandates 164 days, the PM knows they must immediately pivot.
So if the sample size is unrealistic, the PM's immediate responsibility isn't to start coding, but to stop, adjust the MDE higher, or change the success metric to a higher frequency event. You adjust the goalposts to fit the available time and traffic.
Or, if the feature truly requires that low MDE and high N to be profitable, they scrap the feature because the cost of validating it exceeds the expected return. The required sample size is an economic filter.
Let's reiterate the difference between the two types of significance, as this is where strategic confusion often arises.
Statistical significance is the question of reality. Does a difference exist, and is it non-random? This is answered by the p-value. It is the gatekeeper of scientific truth.
And practical significance.
Practical significance is the question of value. Is this difference, the MDE, large enough to justify the entire ecosystem of costs associated with building and maintaining the feature? This is the business judgment.
PMs have to confirm both.
They must. A 0.1% uplift might be statistically real with a p-value below 0.05, but it is practically meaningless. A 10% uplift might be practically vital, but if it came from an underpowered test, it lacks statistical significance and should be treated as noise. You must have both.
The evaluation of trade-offs is where the art meets the science then.
It is the ultimate balancing act. The fundamental trade-off PMs evaluate every single day is speed of learning versus sensitivity of results. The MDE is the direct lever controlling this balance. A low MDE demands a massive N but gives high confidence in marginal gains. A high MDE gives fast answers but risks blinding the team to meaningful, smaller improvements.
This deep dive has really clarified that the power calculation isn't just some statistical hurdle, it's a strategic resource management tool.
It is the engine that generates confidence and ensures resource efficiency. We've established the core loop. Power, usually 80%, guarantees detection, but that capability is constrained by the MDE you choose. And achieving smaller MDEs is exponentially and often prohibitively more expensive in terms of required sample size.
And the necessity of planning the experiment before launching is the only way to avoid wasting valuable engineering time on tests that were doomed to be inconclusive from the very start. Always calculate, always verify feasibility, and absolutely commit to the required N before making a decision.
Use the 4 pillars and let the mathematics guide your product strategy, not the other way around.
To wrap this up, let's go back to the strategic dilemma that's inherent in that power curve. Since small incremental improvements, those marginal gains of 1% or 2% require vast multi-month tests, this raises a crucial question for product leadership, especially in hyper-optimized mature products.
If the marginal gain is so expensive to validate, it forces us to ask, are we better off exclusively running quick, high MDE tests and focusing resources only on genuinely disruptive changes that deliver 10+ percentage points of lift?
Right. If that 1% gain costs 3 months of testing velocity, is it worth sacrificing 3 months of potential learning from other features? Is the cost of being blind to those small wins greater than the cost of slow development cycles and high opportunity cost?
That decision, when to favor speed of learning over sensitivity of results, is the essence of portfolio strategy in a mature environment. It dictates where your engineering budget goes next quarter and really defines the risk tolerance of the organization.
Food for thought indeed. Thank you for joining us on the Deep Dive. We hope this gives you the tools to run your next experiment with true confidence. We'll see you next time.